Hello and welcome to Empowered Learning. This video is the fourth video in the video series for finding zeros of polynomials of high degree. And so this video is actually a part 2 to the Descartes rule of signs video that I made in this particular series. And so what I wanted to do here is showcase how we actually use Descartes rule of signs after we know what our possible rational zeros are, to help us cut down on the amount of work that we actually have to do to be able to find out what these zeros would be. So to start off here, I've already written the function here for one of the examples that we did in the part 3 video, and we already know what this factors out to be, okay? So I'm approaching this as if I don't know what this is going to factor out to be. So I'm going to go ahead and erase this, but we want to keep in mind that we know that -4 and 2 are our actual zeros, and they're the only ones for this particular problem. So if we did not know the answer and we were using the rational zeros theorem, one of the things that we could do to kind of get an idea of what types of zeros we had is we could use the Descartes rule of signs. And so what we're going to do is look at the sign changes of f of x as well as f of minus x. Okay, so of course f of x we'll just write as is. F of minus x, everywhere where we see a x, we put in place of it a negative x. And of course this will give us a minus x cubed here plus 12x plus 16. Now, note here that Descartes' rule of signs lets us know, based upon the number of sign changes that we have in either positive f of x or f of negative x, what's going to be the sort of makeup of our positive and negative zeros. So for f of x, we see that we have a sign change here, and we see we have another sign change here. So what this tells us is that for the positive zeros, we either have 2 positive zeros because of the sign changes there, or if we subtract 2 from 2, we have 0 or none. Okay, so what this means is that in our list, either we're going to have 2 positive zeros or we're not going to have any. Okay, if we look at the sign changes for the f of negative x, we see that we only have 1 sign change here. And so this implies that for our negative zeros, that we only have 1. And again, we only say we have 1 because if I take 1 and subtract 2 from it, I get -1, and it doesn't make any sense for me to say that I have -1 negative zeros. Okay, so that's why I just stop at 1 here. And what this basically lets me know is that when I start figuring out, well, what zeros do I actually have, what I want to do is actually start looking at which negative ones I would have. Okay, because I know if I find a negative 0 in this list, it's going to be the only one. Okay, and so again, using our technology, I'll go ahead and clear this out, and we'll go ahead and put this function back in again. So we'll go to second quit, and then we'll come here and say that this is x cubed minus 12x plus 16. And of course our window, oops, I think I put that in the wrong place. That's right. Let's see if that, nope, yeah, didn't put that in the right place. Sorry, y'all. So let's try that again. X cubed minus 12x plus 16. And of course, our window here will take care of any number in between -16 to +16. So we'll do second calculate. And so now notice here that, again, we're acting as if we didn't have the graph, but the graph is telling us that, hey, we do have a negative 0, and we see that it's only one of them. So here, if we were looking at this, if we went through our list of zeros, we would see that we would find the one at x equals -4 here. So I'm going to shrink what I'm using here so we can actually see the list at the same time here, or at least most of it. So I'll shrink it a little bit more so we can see everything. And so here, if I run through the list, of course I got one. Oh, sorry, want to do the negative. So -1, -2, -3, -4. So here, once I find that I have -4 as a 0, I don't have to try -8 and -16 because I know, according to the Carter's rule of signs, I only have one -0, and I just found it. Okay, so then that lets me know that I need to find positive zeros. And so once I do that, I know that either I'm going to have 2 positive zeros or I'm not going to have any. And of course, if I go through the list of positive zeros, starting at +1, +2, and I see that +2 works, I now have 2 of the 3 zeros that I need accounted for. Okay, and so when I go through this list here, I try out, what is it? Not 3. That's clear. I try out 4. I try out 8. I try out 16, and I see that none of those work. So by using, critical thinking here, I know that I already have 2 of the 3 zeros that I need. Okay, there's one single 0 that's left, and I know it can't be irrational because irrational zeros come in conjugate pairs. I know it can't be complex because complex zeros come in conjugate pairs. So what that tells me is that of the zeros that I do actually know, and those zeros are at x equals -4 and 2, one of these 2 zeros will have to have a multiplicity higher than 1. Okay, and we see that by using the Carter's rule of signs, without us having to try out all of the answers here before we even start to do the synthetic division, we're already expecting that either -4 or 2 is going to have a multiplicity of 2 to round out the number of zeros that we have. So that is how the Carter's rule of signs is actually used to help us to be able to not only cut down work, but to sort of anticipate on what our zeros for our polynomials of high degree actually look like.